All right, let's use this fundamental theorem of calculus part 1, and then we'll do part 2. Part 1, this is sort of the quintessential example. Basically doing the derivative of an integral, you get the function here, 3x cubed. Now, things to note is that we want to have this is exactly like that, and you want to have the number here on the bottom. So if you have anything other than x up there, and if the number's not on the bottom, then when you do this, we're going to have to make some changes using the chain rule and some other rules. So this is fundamental theorem part 1, basically in a nutshell. So what happens if you don't have x at the top, instead it's x squared? Well, what we're going to do is we're going to employ the chain rule. Bear in mind that what we're going to have here is we're going to end up with a function. We're doing the derivative of a function that's evaluated at that point. So the easy way to think about this is that if you have this f and you do the derivative, you're going to get the derivative evaluated at x squared times the derivative of x squared. So this is kind of in the back of your mind when you're doing this. So the way I'd suggest you do this is just think about this as if you're going to do this the way we did this up here. Just rewrite this function over here. But when we do the rewrite, replace all the t's with x squared. But then when we get done with that, we're going to have to multiply by the derivative of x squared. But that's pretty much it. So let's go ahead and do this. It's going to be cosine of x squared cubed minus x squared plus 1, and then multiply by the derivative of x squared. That's it. Okay, things get a little bit more complicated, but not too much. Let's see, up here. Yeah, here. So what happens when the x is on the bottom, the constant is on the top? So in the sort of the standard example, number on the bottom, letter on the top. Here, the letters are on the bottom, numbers on the top. I know pi, it looks like a letter, but it's really a number. So in this case, we're going to, first of all, employ this rule that says that, here we'll do it like this, that if you swap the limits on a definite integral, you just negate the definite integral. And then you can just do what we did down here, and that is do the fundamental theorem. But wherever we find a t, so here there's this t right here. Let me make it a little, there. So wherever we see that, we're going to plug in the function that we have over here, which is tangent of t in this case. And then we'll have to correct things at the end by using the chain rule. But let's do this first. So we got e to the arctan of the tangent of x. And then we have to multiply by the derivative of tangent, which is secant squared. Well, technically, the arctangent of the tangent of x is not equal to x unless x is in the range for arctan. So I'm tempted to write this. Here, I'll do it. I'll just put in parentheses here that x is between pi over 2 and negative pi over 2, which is the range of the arctangent. So if x is not in this range, then it's a little bit more complicated than that, but that'll do. If this was an exam, you would just write this down and be happy. Okay, last one for this, then we'll go to fundamental theorem part 2. So here, what do we do? Well, what we're going to do is we're going to separate this into two integrals, and you can pick any number you like. So I'm going to just pick the number 7, 3t squared, but you can pick whatever number you'd like. And basically what you're doing here is you're imagining, remember that a definite integral is just an area. So you're imagining that what's happening is you've got this function, and here's, let's just call that a and b, And instead of doing the area under the entire range there, you're going to cut it in, cut it somewhere in between. And do this one first, and then do that one. So that's all we're doing here. So this is plus the second one goes from 7 to the square root of x. Oh, that's the fourth root. 3 to the t squared. Now, of course, with this first one, we're going to have to flip this thing around. So let's do that. And in fact, let me just write this one first. Okay, there. Took me a minute. Had to focus. So I just I just did that. Flipped the integral and moved it so that it would be put the negative 1 second. Now I can go ahead and do this derivative. We're going to use the chain rule each time, so it's going to be 3 to the, in this case, square root of x squared times the derivative of square root of x, which is 1/2 x to the negative 1/2. And then the next one is going to be 3 to the fourth root of x squared. And here we have to do 1/4 x to the negative 3/4. That's pretty much it. You could clean this up, but why? Let's just leave it like that. Okay, fundamental theorem part 2. It basically says that the area under a curve is equal to the integral. That's all it is. And so essentially what you're going to do is you're going to actually just compute this antiderivative. The area under the curve is, you can compute that by using the antiderivative. That's what fundamental theorem part 2 says. So we do this, we do this, t cubed, and we're evaluating this from t equals 1 to t equals 3. And so that gives you 3 cubed minus, do the upper limit first and then the lower limit. And so that's 27 minus 1, which is 26, done. Yeah, so this is like the easiest thing in the world. And then this one, just a little bit harder because you have to know your unit circle, but it's not that bad. Antiderivative of sine is negative cosine. Now let's plug in our limits. So we're going to plug in the pi over 3 minus negative cosine of 0. So let's see, that's going to be, the cosine of pi over 3 is 1/2. And then double negative. Oh, why am I boxing that? Let's box this. All right, that's it. Hopefully this helps you. Don't forget to like and subscribe.